All right, so let's take a look at functions and graphs. So a function is a rule from a set D to a set R, where D represents your domain and R represents your range. Sometimes we think about it as input-output. We think about it as independent versus dependent variables. You've probably seen this picture before, where you have an x, an independent variable that's put into the box, and then some action is performed upon the box that results in f of x, the literal function being acted upon the independent variable. You might see these mappings as well, where we have our x's on the left-hand side being mapped to our f of x's on the right-hand side. This specific example would be one of a function. This one works because you can see there's three different points on the left are mapped to values on the right, but there isn't a case where one of the values on the left is mapped to two different values on the right, which I'm going to show with this counter example of a function here. You can see that first point could get divided up into two different cases. So that would be an example of something that is not a function. It would be called a relation. You should use relation when you're talking about things that are not functions. Now, I think that these types of explanations of functions are a little overused at times and can be kind of confusing, honestly. So if you'll bear with me, I prefer to go with what I call the soda machine analogy. So here you've got your options on your soda machine. You got your A1, you got your A2, we know how it works. Now, let's say that you click the A1 button after you've paid and you get a water from your soda machine. You click A3, you also get a water. Sometimes that happens with those soda machines. They're just stocked with water and, many ways you can get to the water bottle. That's totally legitimate. That's a function. That works. A1 and A3 can both give you water. What would be an issue is if maybe that A4 button, well, you click it on one day and it gives you a water, but you click it again and suddenly it's spitting out a soda. That doesn't really make sense. That doesn't really happen. That's because that's not a function. You can't have a situation where you have an input and then two different outputs for that same input. It just doesn't make any sense. It doesn't work that way. So for me, this kind of helps whenever I think about what is a function, what isn't a function, instead of trying to memorize all those drawings of maps and whatnot. Now let's just shift gears here to talking about using certain notation. We've got three intervals on the left-hand side, three different number lines. And in the middle, what I'm constructing right now is just your traditional kind of set notation for how to represent the intervals. Use x in the middle. We always write the less than sign. You guys have seen that before. Make sure you're familiar with interval notation as well. So with interval notation, if you have a point, if a point is included, you use a bracket. If the point is not included, you use the parenthesis. So it's kind of the same thing as closed circle, open circle, with the exception being infinity. Infinity is not a point. You can't get to infinity, so if you have any infinities in your interval, you're going to always use parentheses with infinity. All right, so what we're going to do here is we're just going to run through these examples, and I just identify the domain and range for each of these cases. I might have to squeeze some of this writing in if I want to fit it, but we'll make do with what we've got. So for the first example, the domain is all real numbers because any input is possible. And when you multiply any number by a fourth and add 3 to it, any output is also possible. So all real numbers works for both the domain and the range. In the second example, we have an issue because the variable is on the bottom. We know that we can't divide by 0, so 0 cannot be included in our domain. And the range is the same thing, but for a different reason. The reason that 0 isn't included for the range is because, you have a fraction, 1 divided by some quantity. You can't take 1, divide a number, and get 0. You can get any other number, but you can't get 0. So we'll use the same approach for example 3. Again, we have an x in the denominator, so we know the domain can't include 0. For the range, it's a little bit different. For the range, think about the principle that we used last time. We know that 1 over x can't be 0, but then we're adding 3 to it. So now we're really saying that our fraction plus 3 can't be 3. So there's no way for that expression to work out to be 3. So our range is negative infinity to 3, and then 3 to infinity, not including the 3. Example 4 is a radical function. You might remember square root functions like this. The rule for square root functions is that the inside of the radical has to be at least 0. So in this case, we need numbers that are from 0 to infinity. and that works for our domain. For the range, it's the same thing. If you start thinking about plugging in numbers like 0, 1, 2, you'll see how the range gives you the same set of values. And if there's any shift there, obviously that would be affected. Even odd functions. So this is not referring to the even odd degree of the functions that we looked at back in Algebra 2 when you thought about, like, how your polynomials are going up and up or down and up and all that stuff. This is talking about the function themselves being defined as even or odd. So let's just go through those definitions. An even function is defined as being symmetric about the y-axis. Think about your standard parabola y equals x squared. It can be reflected over the y-axis. Odd functions are defined as being symmetric about the origin. So let's just go through these definitions and kind of look at how they work. Let's say I have some function f of x. You can imagine a sequence of points on that function f of x on that curve. So if we want this function to be even, we need it to be symmetric about the y-axis. So you guys can all visualize what that's going to look like as I draw it in here in purple. Now I have what looks like an even function. It's symmetric over the y-axis. But what we need is an actual rule for calculating even functions. So suppose that the point exists x comma f of x on the right-hand side. What is true about that point that's reflected over the y-axis? Well, it's negative x, and then it has the same height, right? So the key here is that for both x and negative x, we need the function to have the same y value. And that's going to give us our definition for an even function. So let me just write it out. A function is defined as even if f of x is equal to f of negative x. In other words, if the heights are the same for an input of x and an input of negative x. Now let's take a look at an odd function. So an odd function is symmetric about the origin, which means a 180-degree rotation, which again you can visualize here in blue. So this one's a little bit trickier. I'm going to erase the even function we had established just so it's a little easier to read. So we still have our x comma f of x on our right-hand side. We have to think about what that would mean corresponding to the left-hand side in order for this to be an odd function. So let me just fix my graph a little bit so it's a little bit more accurate. Let's see. I'm going to put x, or negative x I should say, right about here. So that's negative x. So what can we say about the heights at x and negative x? Because they're not the same height anymore, but they do relate to one another. So the idea is that we want this point on the right-hand side to have the same height as the left-hand side, but it won't have that unless we reflect it over the x-axis, unless I visualize dragging that point down. So if I was to reflect that point over the x-axis, I would be really finding negative f of x, right? Because I have the f of x y value, but I multiply it by negative 1. That would give me the same y value as negative x would have. So in other words, in order to have an odd function, we need negative f of x to be the same as f of negative x. So you might remember those definitions from pre-calculus or even Algebra 2, but that's just kind of a quick summary of where they come from. Hopefully that makes some sense. And in general, when you're approaching problems that are asking you about even and odd functions, what I would recommend doing is just finding 3 things and comparing them. There's only 3 things that you actually need to find, and just by comparing, you can figure out if you have even, odd, or neither. So the first thing you want to find is f of x, which is usually given to you. So you'll have f of x right out of the gate. You also need to find f of negative x, which means plugging in negative x into your function and seeing what you get. And you need negative f of x. And it's just kind of a matter of matching them. If you notice that f of x matches f of negative x, then that means that you have an even function. If you notice that f of negative x matches negative f of x, that means you have an odd function. And if you don't have any matches, then that means it's neither even nor odd. And that's one of the reasons I don't really love the terminology here, even, odd, because usually when we think about the integers, everything is either even or odd, but in this case with functions, you can have a function that's neither even nor odd. Hopefully this overview of functions helped remind you guys of the basics as we start to review for calculus.